Hello students, this is Dr. Ben, and we'd like to work on another problem out of Chapter 5 that has to do with circular motion dynamics. Here we have a situation that involves a person riding in a carnival ride, the loop-de-loop, and so this particular circular track is oriented in the vertical direction. So it's going to be a problem that involves vertical circular motion. Alright, so let's read the problem a little more carefully and make a list of what we know and what we want to find. Alright, so a person, 60 kilograms, I'll write that down, the mass. It rides a loop-de-loop along a path of radius 16 meters. That's the radius of the circle. At what speed must the person be traveling at the top of the loop so that when the person is inverted, that the seat exerts a force on the person equal to 1/2 of their weight? So I'm given the value of g being equal to 10 meters per second squared. The normal force that acts on the person at the top we want to be equal to 1/2 of the weight. So that's what we're told, and the property that we want to find is the speed of the ride in order for the normal force to have this size. Alright, so let's draw a diagram of the top part of the loop-to-loop, and put the person on it so we can figure out the forces that act. So we'll put the person up at the top. Alright, so it says in this situation that the person is inverted. So that implies that the seat is above them, and so the normal force is going to point in the downward direction. So it's almost like a book being pushed against the ceiling. So the normal force at the top points in the downward direction, as well as the weight of the object, because the ground is below. And if that dot represents the center of the circle, then the centripetal acceleration has to point downwards in our situation. And if I wanted to draw an arrow that represented the velocity, for example, if we pretend that this ride is rotating counterclockwise, then that velocity would point to the left at this instant, and that would be a 90-degree angle with the radius, because the velocity is along the tangent. Alright, so let's go ahead and try to apply Newton's second law and some of the information that we know about circular motion dynamics in order to figure out what the speed is of the ride so that the condition happens that we were asked to find. So the normal force at the top is equal to 1/2 of the weight. Alright, so I'll write down Newton's second law, that the acceleration is equal to the net force divided by the mass. And we want to apply this to the person, and we want to apply this using the coordinate system that we've established, where essentially the positive direction is going to point down, which is towards the center. So the acceleration will be written then as a sub c, and then we can see from the diagram that the net force will be the sum of the normal force at the top plus the weight. And then I would divide that by the mass. Alright, I can remember the formula for the centripetal acceleration, and I can either use the v squared over r or the omega squared r version, and here I'm going to use the v squared over r version because we want to find the speed. So I'll write that down. So I have n top plus mg divided by m. And so I just need to do 2 more steps of algebra, I think, in order to isolate the symbol for the speed. So I'll cross multiply. V squared is equal to r times n at the top plus mg divided by m, and then v is going to be the square root of that quantity, r times n top plus mg all divided by the mass. All right, so we can go ahead and put in our numbers. So the radius was 16. The normal force at the top is 1/2 of the weight, and I would add that to the weight. So I would have 1/2 plus 1 is 3/2 times the weight, which would be m times g, and then that gets divided by m. So I have the square root of 16 times 3/2 times g, because we see from above that the m's on the numerator and the denominator cancel out. So 16 times 10 is 160, divided by 2 is 80, times 3 is 240. So I take the square root of 240 and get my calculator out. 240 square root, and that equals 15.5 meters per second. All right, so we don't sometimes have a very good sense of the order of magnitude of metric units, and 15.5 meters per second is actually around 30 miles per hour. We approximately double that in order to convert it to miles per hour. So this loop-to-loop ride is pretty fast, 30 miles per hour. And just to bring this problem to a conclusion, I'll double check that I have my units. So I have the speed measured in meters per second, and my significant figures, I didn't keep way too many. I maybe should have rounded this to 16 meters per second. All right, so that's going to be the speed of the ride. So when this person is inverted at the top, the normal force acting on them is equal to 1/2 of the weight.